On behalf of 24houranswers.com, I welcome you to today's lesson. In this video, we're going to look at one-sided limits without a graph. You might not have the graph given to you in your textbook. Well, there's nobody telling you that you can't make a graph, so that's going to be for the first example. We will make a piecewise function. And then for the second example, it is slightly different pieces over here for our x and our piecewise function, but I want to motivate you to try to do these without making a graph. You can save a lot of time versus making a graph and not making a graph. So back to this first example here, we have a piecewise function and we have three questions. We want to find the limit as x approaches 1 from the left of g of x, which is this piecewise function here. Then we want to find the limit as x approaches 1 from the right, same function. And then finally, the limit as x approaches 1 of g of x. Well, maybe you know how to do this, and it does revolve around approaching from the left and the right, and it deals actually with this piece over here, because notice we have the ones here as well, like we have in these three examples. Well, before we dive into it, let's review how to graph a piecewise function. 2x, negative 2x plus 3 here, graphing this line, that has a y-intercept of 3. So we'll put a little dot at 3, and the slope is negative 2, so we can go down 2 and right 1. And if we keep doing this, we actually do not want to go in this direction too far. But we can also go up 2 and to the left 1 a few spots, just to kind of get an idea of what the line looks like. However, we only want to see this line for values of x that are less than 1. Sometimes you may see a comma in between the function and this little domain restriction. So I only want to see this line when x is less than 1. So here's where x is, equal to 1, and I want to see the line for values of x that are less than 1. All these values of x here are less than 1. Well, over here on this end, we will put an open circle since we're not equal to 1. So a little something like that. That's our first part here. Now I definitely need to erase these dots here because those values of x are not less than 1. That's why my line did not go down here. Now the second part of our piecewise function is x squared. This is a parabola with a vertex at 0. Thinking back to your college algebra days, probably when you were graphing parabolas by hand. So we have a parabola with a vertex at 0 and, plugging in 1 squared is 1. 2, plugging in 2 squared, we get 4. Plugging in 3 squared, we get 9. So 3, 9. And we have this parabola going on here. I don't want to start at the vertex because I only want to see this parabola when x is greater than or equal to 1. So here is where x is equal to 1. Notice I'm coloring that dot in, and this curve actually goes up something like that right there. So let's erase this green dot, and now we have our piecewise function graphed. We have a line and a parabola here. So looking at the graph, we can evaluate these pieces. The first one, letter A, the limit as x approaches 1 from the left. So we're approaching this x value of 1 here, and we're coming from the left, which means we're on this line. So as we come to 1 from the left, our y value is also approaching 1, right? Remember that open circle we did? So that's our left-handed limit. Our right-handed limit, the limit as x approaches 1 from the right, that's going to be this parabola because the parabola is on the right side of 1. Well, regardless, as we approach an x value of 1, our y value is also approaching 1 as well. And from previous videos with one-sided limits, if the left-handed limit is equal to the right-handed limit, then the limit exists. So therefore, the limit as x approaches 1 of g of x is equal to 1. Now, to motivate the idea to get you to do this without making a graph is to look at these domain restrictions. If x is approaching 1 from the left, we want to use, and it's all about this right here, x approaching 1 from the left, we want to consider values of x that are less than 1. Because values of x that are less than 1 are going to be on the left side of 1. That's why we dealt with the line. So all you really have to do here is take 1, plug it into this line here. Negative 2 times 1 is negative 2 plus 3. We get 1. Direct substitution works great here. This does not always work, but as an introductory tutorial, this will work just fine for both examples that we're going to cover in this video. Notice this one, the limit as x approaches 1 from the right. As we approach 1 from the right, we're talking about values of x that are greater than 1. Sure, it says greater than or equal to. That equal to there corresponded to that closed circle. But x greater than 1, that's going to be values of x that approach 1 from the right. So we can take 1 and plug it into this function, and 1 squared gives us 1. So we never really needed the graph. And with those things in mind, and again, since the left-handed limit is equal to the right-handed limit, the limit does exist. Let's look at the second example. We had the same two pieces in our piecewise function for the second example, but notice we have a different domain restriction for these x's. X is less than 2 and x is greater than or equal to 2. And our function is now called h of x. So recall, if we approach a number from the left-hand side, we're talking about approaching that x value of 2 from values of x that are less than 2. Approaching from the left means we are approaching from values of x that are less than 2. So we're talking about this piece here. So let's take that 2 and let's plug it into this piece right here. Negative 2 times 2 is negative 4 plus 3, we get negative 1. That is our left-handed limit, just like that. As we approach 2 from the right, we're talking about approaching 2 from values of x that are bigger than 2. Notice here, x is greater than or equal to 2. All I really care about is the greater than piece. Let's take our 2, let's plug it into here. 2 squared gives us 4. That's our right-handed limit. And therefore, since the left-handed limit is not equal to the right-handed limit, the limit as x approaches 2 in general of h of x does not exist. And again, we did all of this much faster versus us creating the graph. By all means, you could do this. And I tell you what I want to do to sum up this video. I'm going to take this graph here and I'm going to modify it a little bit to match with this second example. So there it is, the modified graph. It's the same line and the same parabola. However, notice I have modified the line such that we see the line for values of x that are less than 2. In the previous example, notice that we did have this thing stopping when x was 1. Now I have this line stopping when x is 2, and I have the parabola starting when x is equal to 2, as you can see there. And notice these limits. The left-handed limit, we said it was negative 1. Well, notice that is the y value that we are getting close to as we approach an x value of 2. That open circle has a y value of negative 1. Even though the function's not defined at that particular spot, the limit still exists. The left-handed limit, that is. Then, as we approach 2 from the right, coming in from values of x that are bigger than 2, look at the y value that we approach on this parabola, a y value of 4. Notice that right-handed limit was 4. And since the left-handed limit is not equal to the right-handed limit, we said the limit as x approaches 2 does not exist. And that's it for this video. I hope it helped. Be sure to check out our YouTube channel for more videos. Links to our social media are in the description below.